Among the different particles which are present in the cosmic rays, we haven't discussed so far the antiparticles or antimatter that is also present. So this is the final section of B1, antimatter in cosmic rays. And we'll be talking mainly about the positrons and the antiprotons. There is actually some detections also of heavier species, like for example antideuteron, and even some heavier stuff, which however is very small numbers and is not really conclusive yet, but I think this is something which will probably be maybe a major result of the upcoming years, that there will be a firm detection of heavier species and maybe also some clear measurements of, for example, their energy and so on. Now, first of all, it's not surprising to find positrons and antiprotons in cosmic rays. After all, this center of momentum energy is sufficiently large to produce in the inelastic scattering matter and antimatter in equal amounts. So that's not really surprising. So let's call this the conventional origin that is well expected and also has been observed. So that would be for positrons simply inelastic scattering. So cosmic ray proton, and again take it as a representative for heavier nuclei as well, with a proton of interstellar medium, again also heavier ones are of course targets, will do inelastic scattering. And in the process you produce, in most cases, for example, charged pions, and if you create a pi plus, this one will decay into a mu plus and a muon neutrino, and the mu plus will decay eventually into a positron, an anti-muon neutrino, and a electron neutrino. And of course you have various final states, but many of them will contribute into this positron production. For the antiproton, and this one doesn't actually, the production of positrons doesn't require a very high center of momentum energy. It just needs to be sort of at the level of a pion. So it's 100 MeV, which you need on top of the rest mass. So this is small. It's not much problem there. If you want to create a proton, an antiproton, however, this situation is energetically a little bit more demanding. So you got, again, let's say, inelastic scattering. And the final state that can contribute to this has to, of course, also maintain baryon conservation. So basically, if you have proton-proton coming in, you have to have a proton-proton in the final state. And in order to create an antiproton, you need to create another heavy proton, right? So that's sort of the minimum type of final state that you can do to create an antiproton, and therefore it requires a higher threshold energy. Now let's look a little bit more detail into the positrons, because that's a bit more interesting, because there's been also some deviation. So what's the predicted spectrum that you can get? So the positrons are assumed that they only come from secondary processes. So we assume that at the source there's no positrons accelerated, which we will discuss a little bit in a moment about the validity of this assumption. So let's assume we call this the flux of positrons phi plus. This will go with gamma to the minus 3.7. So gamma is the Lorentz factor here of the positron, essentially the energy of the particle. Now, why is that the expectation? So let's just go through a very simple argument. Let's assume we have a simple model where we assume that the production is happening in equilibrium. So we say this partial derivative of phi plus t should be 0. So losses and gains are basically balancing each other. And then we can have essentially some injection process, which will depend upon the Lorentz factor. Plus, and since there is no spallation or anything, the only loss term we have is continuous radiation, mainly radiative energy losses, which will be of our concern here. So if we go back to our equation, we have such a term which looks like this, gamma dot times phi. So gamma dot is the energy loss term. And so Q of gamma is the injection. So that's essentially how positrons are produced, and that's through interaction scattering with the medium. So Q of gamma will be following the, with some constant here, will be following essentially the index of the cosmic ray energy distribution. So this will go with gamma to the minus s plus delta. Keep in mind delta was this energy dependent loss term, and in my case I defined it to be negative, so delta was something like minus 0.5, and s would be something like 2.2, so that the whole thing becomes like gamma to the minus 2.7. And the energy loss term, this one here, gamma dot, I just write down as something like minus b gamma squared. That's the radiative losses. So that's mainly synchrotron. There could be also some additional contribution from inverse Compton, but in the B field of the galaxy that will dominate. And so then B is proportional to the energy density of the magnetic field, so that's going to be proportional to B squared. So if we put everything together, then we have a very simple equation which we can solve by separation of variable, and then we get for phi plus, we get 1 over b gamma squared. So we just basically separate the variables out, and then we basically integrate by gamma the q, because that is supposedly depending only upon gamma. And then we have to divide by gamma dot, and that basically gives you 1 over b gamma squared with a minus sign, and basically becomes positive. And then we just integrate here over gamma prime, q of gamma prime, with some initial value of which we don't care about here. We just want to know what the distribution will look like. And so since q of gamma is gamma to the minus 3.7, we integrate with gamma, so we get gamma to the minus 2.7, and then we have divide by gamma squared. That gives you then gamma to the minus 2.7 integrated, gives 1.7, sorry, gamma to the minus 1.7. So this gives proportional to the gamma to the minus 1.7, and then we divide by gamma squared, so this thing goes with gamma to the minus 3.7. And that's essentially what I was saying in the beginning. So the spectrum will go 1 unit in the power law index softer than the actual cosmic ray spectrum. Now for the electrons, we can safely assume that electrons are being accelerated in the sources as well. Think about our shell-type supernova remnant. You will have ionized material there, so you'll have the nuclei and the electrons. The electrons will also participate in the acceleration, and with some fraction of the electrons will actually get accelerated. So there we can basically just do the same kind of logics, but now we replace the injection function with something which is just the source for the electrons, and that will inject with minus s, because that's the initial injection spectrum, which will be the same as for the protons. And then we will have also a secondary process, and let's call it Q0, because you will produce roughly the same amount of positrons and electrons in the cosmic ray interaction with the interstellar medium. And then we just have here our term which we just discussed before, minus s plus delta, so that's the same thing. And so this is essentially the accelerators which will contribute directly, and then this is the contribution of secondary interaction. And for the electrons, well, for the positrons, we assume the accelerators do not contribute. We assume only that the electrons are being accelerated, and we also assume that this is dominant. So this will be the dominant term. So we basically neglect the secondary component here, but in principle it should be also present, but it should be much, much smaller. So then we can do the same thing, and then we find phi minus is proportional to gamma to the power of minus s plus 1, s minus 1, sorry, not plus 1, or I should put a parenthesis there, minus s minus 1, because in the same way we do it here, our q of gamma is gamma to the minus s, so we integrate over that one, so we get minus s plus 1, and then we divide by gamma squared, so we get minus s minus 1. Okay, so that means that it's just one index softer than the 2.2, and so this should be roundabout gamma to the minus 3.2 if s is 2.2. And that should be dominating over the positrons, which go with gamma to the minus 3.2 for the phi plus. Okay? So that should be, I should maybe write it this way, should be dominated by phi plus, which goes with gamma to the minus 3.7. So you see that they do have different indices, and now we would just want to compare the ratio. in a moment, but first let's have a look at the overall particle spectrum. So let's look at phi minus plus phi plus as this measured, and let me just pull that in for you. So what you see here is now this is as a function of energy, the combined flux. So this would be actually phi plus phi minus times gamma to the power of 3. So that's just to make it this as drop not so strong and to see more the shape of the spectrum. And below roughly 10 GeV or so, we are basically dominating affected by solar modulation. Remember, that's the solar wind which drives out the cosmic rays out of the interplanetary space at low energies because they are being advected away. And then if you look at this slope here, this is the line I drew in here. This is roughly the gamma to the minus 3.2, which you expect to see from the pure electron spectrum. And you see, however, that the actual measurements show some excess here. So this goes above this here, and then it basically comes down here, and then it follows a power law. What you do expect in principle is that the electron spectrum should cut off at some energy because of the maximum energy that is feasible. So what's this excess about? And it becomes even more clear if you now look at the actual ratio of positrons to the all-particle flux, because with some of these experiments, like for example Pamela and also AMS, you can determine the positrons separately from the electrons. And then you can do a comparison by looking at the fraction. So that would be the positron flux divided by positron times plus the negative one. So that's exactly this plot up here. And then basically also the effects of solar modulation cancel out because they affect the positrons and the electrons in the same way. Let me just pull in again the figure for this. So this is the ratio. So that's this quantity which I just wrote down as a function of the energy. And you see that the number is roughly 10%. So positrons make out about 10% of the electrons. So that means that pretty much 10 times more of the stuff is being produced in the direct acceleration, and then the secondary component is only roughly 10%. So that verifies our assumption. And you see that this fraction basically drops here as you expect it to be, because we had said that the, so this one goes with gamma to the minus 3.7, and this one should go roughly with gamma to the minus 3.2. So it should go down with gamma to the minus 0.5. And this is pretty much okay. So you see roughly about the factor of 3 that it goes down over 1 decade of energy. So this is actually the way that it should become. However, you see all of a sudden that the positron fraction rises above roughly 10 GeV. And that's also consistent with what we see here. If you look at 10 GeV, that's about here. You start seeing that the positron, that the overall flux goes above this power law expectation that we derived in our simplified model. So this means this is again an excess, and it's really an excess of positrons and not just that the electron spectrum behaves in a different way. And that's something which needs to be understood. Where does this excess come from? And so this is certain, and you also see that this excess seems to turn down. So the last data point here seems to be indicating that it goes down again, so that maybe the excess starts to become less pronounced at higher energies. And at these energies, there's no direct measurements of positrons anymore, but we can still look at the total flux, and we see that the total flux sort of falls down here, but there seems to be maybe some other excess even here, which we didn't touch upon so far. So what are the possible explanations? This is essentially just two of them which you can consider for the positron excess. So let's talk about the conventional one first, because I think that's quite easy to identify that there must be something maybe in our assumption. So we assumed in our case, in this very simplified model, that positrons are only produced through only secondaries. And that's of course an assumption which can be questioned. In this case of the supernova remnant, it's very difficult to understand where the additional positrons would come from, but even there you have a source of positrons, simply given that, for example, in the case of a supernova type 1, You do have a lot of nickel, which does a beta plus decay, so you do get some positrons injected there, and they may be started to be accelerated as well. But there's of course another source type, which is the neutron star, and neutron stars accelerate electrons and positrons in equal quantities. So what if you had now an individual source or sources which produce positrons, and they are accelerated and they come towards us, and it would then produce such an excess, because they would be adding on top of the secondary produced positrons. And that's sort of the main gist of this conventional explanation. You need a local. Local means that since this excess is good up to several hundred of GeV, maybe even up to TeV energies, you need sources which are not too far away, so that the positrons do not lose their energy so quickly. In principle, if you observe a TeV electron, you cannot get this electron from any source which is further away than sort of a kiloparsec, because it would have to have started with an infinite large energy to get there with us with still 1 TeV energy. So the distance should be less than roundabout a kiloparsec positron source, or sources as a matter of fact, so there could be multiple of those. And candidates would be, for example, neutron stars, aka pulsars. They would be able to do the job. There is, however, also one additional point which can be checked. So in this case, you would expect, since the sources have to be local, either you have many of them which overlap in such a way that they appear isotropic, or you would have maybe one, maybe two sources which sort of would produce an asymmetry and anisotropy in the distribution of arrival directions. So a good check of this is that there's a predicted anisotropy, and this is ongoing because you need more statistics. You see here you have only few positrons, and it's difficult to make a test on the isotropy of the whole sky with only few positrons there. And the second possible explanation is the not so conventional ones, and that is that we have self-annihilating dark matter. So this is something that we will talk about more in the next section, where we discuss dark matter. But the basic idea is quite simple to understand. You have massive particles, which could also be the main constituent of dark matter that we observe in our galaxy. And if they self-interact, they will produce standard model particles like fermion, anti-fermion pairs. And that could be also producing in the final state eventually electrons and positrons in equal amounts. And therefore you would then expect to see positrons in excess to the ones that you expect from the simple cosmic rays of the galaxy. And then you could basically explain that quite well. So that's quite reasonable. You would need only that the mass of the dark matter particle should be larger than at least 500 GeV, because in order to get positrons at 500 GeV, which is sort of the peak here, even beyond, you need to have sufficiently massive dark matter particles to produce that energetic electrons and positron. There's a lot of caveats to that, and the main one I just want to mention here is that I mentioned at the beginning the anti-protons, and as it turns out, the anti-protons, they should also show an excess, because when you produce particles, antiparticles, quark-antiquark pairs, you should also produce antiprotons in the final state through this annihilation process. And so there's no excess seen in the antiproton, and that's quite constraining. That means that you need to then think about some particular dark matter model where the self-annihilation prefers in the final states to produce leptons like electrons, positrons, and maybe muons, but not so much antiprotons, which you need some quarks for. So that's like we call this leptophilic dark matter models, which is a little bit difficult to pull off, but not completely impossible.